Okay, give me 1 second while I don't know, get myself. I guess there's not a lot to get ready. Okay, so are we sharing?
Oh,
okay. And we're all on. Yeah. Okay.
Let's steal this side. Let's see. I think I'm supposed to hide the video window. That was the trick. Because last time we were capturing the
video
window.
Video and the video.
Yeah.
Do you want to share?
Do you want video too?
I'm gonna play video.
Okay.
A quick video, but
let's do that. Video. And then looks like no video, so I think we're good.
Okay. So I can't see all yous at home, so if somebody's got something to say, just speak up. This all started when my dad dropped his lobster stick in the Indian Ocean. And for anybody that doesn't know what a lobster stick is, it's like a temporary anchor for when you're diving. You like stick it in the sand if you're at the bottom and there's a current, or you can use it to kind of claw your way up. I think it was originally used to like go find lobsters or something. I have no idea. So my dad and brother dive, and my dad dropped this in the ocean, and he's like, "Hey, you have a fancy machine. Why don't you make me one of these?" And so this is what he sent me. And in an, like an arms race to impress my father, I decided to take on that challenge. So I'm writing this. I'm kind of doing this presentation as somewhat of a high-level tutorial on like the question of I have a thing. And I want to make it on a CNC machine, like how do I go in between? And so I happen to have, he sent me a really nice picture and told me that the handle is 4 inches long. Whatever that means, we'll learn as we go. And so anyway, so the first step was to crop down the image and get it into, so I use Fusion 360 for all my CAD CAM. I assume this is all, relatively the same from other CAD CAM options. So the first thing I did was scale this to about what I thought and then lay the image on top of it. I've changed some scaling before I got ready for this presentation, so some things might look a little out of place. But when I first started, that box would have been 4 inches long, and that canvas would have been, that decal would have been stretched on top of it. And so I used the decal. I've since learned that you can just lay a canvas on this, like onto a sketch plane, and then scale it that way. I didn't use that method. I just kind of extruded a body that was about the size of the handle, and then kind of laid that image on top of it like a decal. I didn't want to bring my work computer and get wrapped up in work and all that, so I'm just doing kind of a slide presentation. But I absolutely will answer questions even offline about this process. It's kind of my new hobby, so I love learning and talking about it. So I laid that down, and then the next step, and this is something that took me a long time to figure out, and so it's really simple. It's like it shouldn't have taken me this long, but I recorded a video kind of redoing the steps I originally did, just so I can show everybody what that process is, because it's like, it's all goofy shapes, and I've done so many times where I've like laid different arcs and tried to make them match, and then once you lay 40 different arcs and trying to get them to merge together so that your software will understand it. And I've since learned a much better way to do it, which is using the, I think, I deleted that screenshot, but you'll see the tool that I use here. And so basically, once I, created a sketch on that plane, then I'm using I think it's going to pop up here in a second. It's the tool up, right there. And it's I can't remember the name of it. Spline tool, yeah. And so I just kind of willy-nilly picked spots that were roughly on the outside. Fortunately, this isn't a high detail thing. It's just a handle, right? So if you're trying to duplicate something with dimensions, then you would have to get a little bit more crafty with what you're doing. The original was an injection, like a dual injection molded contraption. So I just kind of erased a bunch of the details and just went for the kind of overarching dimensions, the shape of what I'm doing here. And the cool part is all of this part only took me like an hour. Granted, I've been doing CAD for a couple of years now and kind of learning as I go. The CAM actually didn't take that much long either, but the trial and error of getting all my tool paths and my fixturing, and I don't know how many of you have done much CNC work, but it's like 90% setup and 10% watching the machine do the thing. It's similar to welding in that way. I also only weld with like painted bullshit metal that I found on the side of the road, so I don't really know what it's like to like pull a brand new stick of metal out and weld it, because that sounds fun. And so once I kind of had the basic shape, then I went back and kind of tweaked everything, and they're all connected. The great part about the spline tool is they're all connected, and like if I move this arc, then it affects kind of after it, and then you can grab, if you see when I click, it has the long kind of adjustment. Huh? Handle.
Those are nodes and handles.
Nodes and handles. See, we're all learning today. And so then I could grab the handle and kind of tweak the various different radiuses that I'm looking for. And again, this one, I was just kind of recording this video just to show you all the process. So I didn't go through all the extreme detail and make it, you know, as close as I did on the original. But that's the basic premise. So once I got all this tweaked out the way I wanted it, then I just kind of had to cap off that end. I wanted a flat end on it. So I just, instead of keeping that spline tool wrapped around, I just used a straight line on that. And as you can see, like my hook in there and the handle is different, I guess, from the final process. But basically, once I figured out how to use the spline tool, my abilities to draw over a sketch just went through the roof. Like I said, it's silly how much time I've spent in my life messing with other ways to do this. And so that's kind of the bulk of it. Yeah, I kind of close off this end, and then now I have like a full enclosed object to mess with. From there, this is the original. This is kind of what I actually ended up using. You can see it follows the contour a little bit better. The hole here, we'll get back to that. I ended up coming back to add a locate hole, and I'll get into that when we get into like a little bit of the machine theory. And so the next thing I'm going to do is I had that block of material, and I just extruded. I cut out the rest of it. And this is another trick, if you guys haven't messed with extruding too much, is here, instead of doing a distance, like the material is 1.3 inches or whatever, I selected two objects, flipped it around, and clicked on the back of that material. So then if I go back later and say, oh, that material is actually 2 inches thick, then it'll re-extrude all the way down instead of just the original like 1.3 inches that I did. So after, yeah, so I extruded, and then I have kind of this body, and then it was crazy. I just grabbed the radius, the roundover tool. What am I? The fillet tool. And then this I just kind of played with until I got it. You know, like I said, I'm not reproducing anything that's going into space, so I just kind of messed with it until the arcs didn't error out. So if you go too far, they start running into each other. And I kind of just picked a shape that I liked. And then I ended up doing it in a few different places. I rolled over that end, as well as this one little, it's a little hard to tell in between, but I was just kind of being futzy with it and kind of getting this little, you know, some of this stuff rounded over so it wasn't so harsh there. And that was it. So now I've got my shape, and then it's like, you know, then you just like, you show it to the machine and it makes your part, right? And that's just how it goes. And so I had a piece of random material from whatever, who knows what, in my garage. And so I kind of measured it out. This is two different screenshots tied together, in case you're curious. And it was about, you know, these kind of dimensions. And so I used that to set my material. Because the machine needs to, oh yeah, that's a good idea. The machine needs to know like what all material you're removing. And then also the big one that if you're new to CNC, you got to pay attention to is your work coordinate offset, or which way is up and which way is left and all that stuff. And so for this is called Op 1 or Operation 1, I pick the top, middle, center of the material. And now I can just kind of probe and figure out. And then from there, you just start kind of laying tool paths against it. The final thickness of the material of the piece that I wanted, I think, was 1 inch thick, and I had a little bit over 1 1/4 inch material. And so the first thing to do is just kind of face off a bulk of material, which is kind of a common operation. And then I'll show you the cutters I'm using. I only use 2 tools for this. And so this is a big roughing end mill. It's 1 inch diameter, 3 flute job, one of my favorite tools to use. And so I just use this to just get rid of material. And you can see the hat on the bottom. It's, you know, you guys are passing them around, but the hat on the bottom is where it's locked into the jaws on the vise. And so that part can't go anywhere in Operation 1. And so once I kind of remove a bunch of material, I come back and do another roughing pass to just clean up more of the material. Because basically to get a good surface finish, you want kind of constant tool engagement. You want your finished tool to be always doing the same amount of work, or else you get like chatter and kind of goofy spots. And so I didn't go crazy with it. You can obviously go silly. One of the fun parts with Fusion is trying to understand why it adds these yellows or linking moves, or where it's moving and not cutting. And if you look, there's a bunch of goofy stuff in here I played around with myself. I messed with it. I got some people at work that are machinists to mess with it. We never really could figure out why Fusion thought it needed to leave and come back again. So, you know, if I was doing these in production environment, I would have spent a lot more time kind of figuring that out, because that's all just wasted space or wasted time, I guess. And so if you look, there's a flat down the center. So the next thing I did was just kind of cut this contour so that that part is solid. You know, I wanted, while I had that cutter out, I wanted that contour to be cut just once from the top, and that was it. And that helps. So one of the things, if you're ever machining and you're trying to get into multiple operations, getting them to line up and not having like a tool mark is huge. And so I opted to pick right here where this seam is, where the arc meets the flat, and that was going to be where my next tool path stopped, so that anything would be hidden kind of in that little area. And if you look, I mean, at the pieces that are passing around, I think it looks pretty good personally. And so then I filed it, so that all was done with a square tool, and I came back with a radius tool to get that edge, because you know, you can't, if you want a nice contoured edge, you have to have some sort of like a ball end mill or a bull nose. I had a 30 thou radius on the tool that I was using. And even here at the end, these are all little circles. It just came off and did a little quick circle and come back around.
So that last operation where you flattened the sort of the meridian there, was that just so you could grab it?
I purposely did that to be one pass, because I wanted a nice, as best surface finish as I could get, where it just went around once, instead of in a roughing operation where it would have come through a bunch of times. And so in all my roughing operations, I left like 20 thou material, and then I came back and did one kind of final pass.
Over everything.
Yeah.
Oh, okay.
Yeah. So that one pass, that one contour was the only time I did that part tightly. You can see the lines here, and that's because I'm cleaned down to finished side. And then and I needed to clean that up, because in Op 2 I'm going to hold it by that surface.
The green is material and the gray is finished. So right where his cursor is with his little against the gray are, that's like the actual size of the part that he wants. And the green is all remaining material, which is where he's cleaning out the ball on the top.
And you can see I'm done with the top here too, because of the contours of the original shape are starting to poke out. Because like if there was any material here, that would just be a green top. Yeah, so then the last thing I did is I just did a real slow plunge with my, that's a 3/8 inch end mill that I was doing the work with. And I just did a nice slow drill operation to punch a hole, because whenever you do multiple operations, yeah, and Dennis, back to your point, if you look, and this is where I got hung up, if you look here, and I can't zoom in because I didn't bring that computer, but all on the top, it just carries all the way around. And then here, for whatever reason, when it got to like closer to the vertical flat, that's when it was like, oh, better do a lap. And so it would come out and come back. I don't know why. And so anyway, so whenever you're going to do a second operation, you always want to locate on a feature that you milled in your first operation, because your material is never going to be true. Your fixture can move around. And so I punched the hole specifically in the waste material so that I can come back and indicate off of that later. And so that's why some of the ones that I'm passing around don't have that hole, because I hadn't even thought about Op 2 yet. I was just like doing a proof of concept cut at first. And then the one that did have a hole, it's like it went sideways on me. I think, I actually broke my cutter on that one. I rammed into a vice jaw because I was like talking to somebody and not paying attention. And so then this is like, so the 4 inches that we talked about, that's this tiny little one that's passing around. I don't know, I don't know, whatever. It was too small.
It's gonna be a good steak knife.
Yeah, right. So I kind of slowly increased it to the size of the pieces of material that I had, and whatever my final size was just based on whatever material I had laying around. And so I took this picture because that's the locate hole. And so then the next step is going to be to flip it and then do all this again on basically the same operation with a little bit of difference, on the other side to get it cleaned up. And so to do that, I had to cut soft jaws. And if you haven't messed with like weird shapes on like square material in a vise, it's like pretty straightforward. In this case, I had these. Oh, I guess it's not in the next picture. Anyway, I had these aluminum jaws that I milled out to this shape. So it's only for this job. You know, I can repurpose them maybe later. And then one of the things that I've learned throughout my kind of dinking around here is that you don't have to have soft jaws that are perfectly contoured to your part. And so one of the things I've learned is to leave relief in a radius like this, because if my tool, if my tool was super sharp when I cut my soft jaws and it made that contour perfect, but then I wore it down through many operations by the time I cut that final part, if that final part's flat, then it'll bottom out in that inside radius, and then it'll kind of sit in there cattywampus. So I try to cut a bunch of reliefs, you know, in where these handles were. This was a wide enough contour that I didn't feel like I needed it here. I'm just making this up as I go along. It might sound like I know what I'm talking about. I'm really just winging it at this point. And so then this is, oh, okay. So then I had to run the cam against the soft jaws, right? And so I set up my operation. I just kind of made up some material because these jaws are attached to the vise. And I ultimately was going to locate on those. And I didn't take a picture of this, but one of the things I did was I clamped this like an 1/8 inch piece of plastic in the jaws when I tightened them down before I started milling them, so that because if I didn't and it held true and then that piece ended up a little small, it would be wonky. So I put in a piece of sacrificial plastic, cut it out with the soft jaws, and then threw that plastic away so that I had some room to close past the object. So when the vice jaws are closed now, there's a little less than 1/8 of an inch of gap in between them. And so then I just kind of ran some tool paths against that, just kind of giving you an idea of the basic operation. Was I did a roughing, and so if you can notice here, there are two different. It's a 2D and a 3D pocket. And in Fusion, the difference being 3D stuff, Fusion kind of figures out for you, and 2D stuff, you have to tell it specifically what you want it to cut. And so I did a 3D operation just to remove material, and I told it to leave a little bit all the way around. And then I came back on the next operation and did a 2D with 0 stock leaf, so they cleaned up all the edges nice and pretty. And I did one depth of cut all the way around so that all my edges were kind of, you know, cleaner or what have you. And then this is the soft jaws. You can see I kind of repurposed them from something else, whatever, there's some holes in them, but ultimately it holds the part, which is what it needs to do. I ultimately also ended up doing 2 sets of soft jaws because I was kind of doing this over the course of a couple weeks and I had to do a few different tests and trials and whatnot. And so one of them holds the part for op 2, and then the other one is for a vise that I stood up ways to drill that hole in the end to shove that rod into. And so I needed kind of both setups going so I can continue on. And then for op 3, and this is an important part, this took me when I first started machining, I got hung on this for a couple days. And so I figured I'd show you guys. The previous, I'm grabbing my material and my stock is from the preceding step. And so you know, Fusion, I'm basically telling Fusion that this is the material I'm starting with. It's not like a piece of rectangular stock or whatever. I'm saying like, where all your math is going to be based on this shape. And then the continue rest machining is the magic checkbox. That's the one that stumped me for a long time. It's like almost doesn't exist, and I got lost. Because just from preceding step, we'll grab the stock dimensions and relationship from before. And so then that checkbox says, grab this shape, you know, what's left of the cutting from the first step. So then the same thing, I just kind of I actually copied and pasted these tool paths down, so you don't have to kind of redo everything. I just grabbed the ones that were important and moved them down. And so like there's a bunch of stuff that doesn't need to happen, like the 2D contour and the drilling. And then I guess the adaptive roughing I didn't do again. And so yeah, so I faced it. I did my roughing strategy. I came back with that radius tool and cleaned it all up. And then at that point, you've got your finished handle, or the semi-finished handle. Next step being to poke a hole in the end for that stainless steel rod. And so then yeah, I'm going to get this, and I didn't show you the 2 holes. That was kind of fun. It's otherwise just kind of standard drilling operations. What I did learn about pilot holes in this, because that stainless steel rod my dad got from some industrial environment, so it's exactly 0.25 inches in diameter. And so I went to my drill index and I grabbed the 1/4 inch drill bit and I stuffed it in there and I ran it down and it wouldn't fit, and I looked and I measured, and it was 0.23 something. It was some other drill bit that was like close enough to a 1/4 inch that I stuffed in my drill index. And so for the first one I cut, I started with a 0.23 something drill bit, and I came back and I measured. That's when I like got the calipers out. I measured everything, and I had a 0.248 or a 0.252 drill bits. And I was like, okay, I'll go a little undersized, a couple thou under, and I'll wedge that thing in. And so I put the 0.248 in. I drilled the hole, and I beat the snot out of that first one to get it in. I put it on a block of wood so it didn't mar it up, and I just beat the ever living piss out of it. And I got it in there. And there's a 1/2 inch. I think I created it. I'm pretty sure if that ever comes loose, it's going to torpedo out of there, because I think I just compressed air into it. Because at some point it just wasn't going any further, and I know from my measurements that I got at least a 1/2 inch of space in it. Yeah. And so I'm waiting for my dad to be like under like temperature change between the different material types, and he's all of a sudden got a harpoon, like somewhere underneath the ocean. I hope that doesn't happen, but that sounds kind of fun.
You need the handle and send it to
Oh, that's a good, yeah.
As long as it's a fish,
Yeah, right. Yeah. Specifically not my brother. I would never hear the end of that. And so anyway, so the reason I'm saying I learned about parallels is because the second one, I was just kind of running and gunning, right? So I stuffed the second handle in. I drilled the hole with the 0.248. Well, there's some wobble, there's some innate run out in that holder or whatever, and the way the drill bit locks and all this. And so I forgot to bring an extra piece of material, but if you stuff the shank down the handle that's done with the hole in it, it just slides around. It's a couple thou over, even though the drill bit was a couple thou under, purely because of just that little walking around in the material and all that. And so for the third one, which is the second completed one, I came back with a smaller drill bit and then stepped my way up.
No reams?
No, I haven't gotten into that yet. I don't have a bucket of those yet. I have buckets of drill bits. I don't have buckets of reams. I should.
Yeah.
You're right.
Yeah, we've got the reams.
Oh, okay, that's good to know.
Get another chat, yeah.
Oh,
Almost always go a little over.
yeah. Oh man, all right. You guys are right.
It's killing you.
Yeah. Oops. So yeah, anyway, I put the pictures on here for the people at home that don't get to see don't get to touch and feel the live thing.
Black title, it's all that.
They
Yeah.
feel really great.
How do I?
Nice. Yeah, they're beautiful.
Thank you.
Is your dad got the
No, I'm actually going to send him this video with the parts, just because I think he might be interested in the procedure.
Is this you turn this into like, I'm thinking sweet corn, stickers? Just gotta put 2 rocks in that.
Yeah.
Nice
Well,
handles.
so the fun fact, if you grab both of them, you're immediately teleported into a comic book.
Yeah.
And like as soon as I was home, I looked at my wife and I was like, I want to fight the Foot Clan. And my wife was like, what are you talking about? So, yeah, the fun part will be getting it through TSA. So this is the, just in case anybody was curious, this is the roughing end mill that I use, which is my favorite tool, because this thing just plows through material. And then, and that's just kind of a square point tool. And then I use the radius end mill to do all the contouring. And then,
What was the threaded end on that?
oh, it's a modular. This is a modular piece, so you can get tool holders that are different lengths in case to like stick it down in a hole or what have you.
So when you're doing something fancy, you might need a tool that's this long, then you might need a tool that's this long. You never want to run a tool this long when you need one that long. So the idea is this fancy bit of the tool then can go on a long stick or a short stick. And that way you can have a super big tool or a short tool.
Is that reverse threaded then?
Probably.
Probably. I don't. Yeah.
When that
It tightens up as it.
Yeah.
Oh, yeah, that's the point. Yeah.
So I'm guessing the little Genmitsu or Genmitsu CNC machine that I bought for like less than $245, probably won't be able to do.
It seems unlikely that you're going to run this tool in it.
You could run the tool.
Oh,
It's
no.
touch it.
I mean, I won't be able to get your result.
Yeah, yeah.
It's also-
That's what I call doing fall haircuts on something. You're going to like 2 or 3 pallets at a time. You're just going to massage it into shape.
Let's say you could get it cut. You just have to take like a few thousand off at a
Yeah.
time.
Yeah.
You're on a desert island. Like,
Is that steel? Is that what that is?
This is all aluminum.
Aluminum.
I purposely did aluminum because it's going in the ocean and whatnot. And I think that's the end of my slideshow. So there you go. Any other questions? More in the chat?
If you enjoy the process.
I've tried the Superfly, Dennis. I'm a big fan. The Superfly doesn't remove nearly as much material and excite the primate inside of me like that the mini shear does.
Anybody got any questions for Davie?
It does make a great
So
sense.
Davie, if you had to bill time
Ooh.
for one of these, how much is one of these worth? So Davie's got his hand pretty, willy-nilly with the thing, stabbing at stuff. How much money is he hanging on to there? All the tooling, all the time.
Well, the tooling tricky because like
I know.
I did mash 3 of those inserts, which are $20 a piece. But that was a user error. I can't bill for that, I don't think.
Yeah, no, that's cool. That's
Yeah.
a prototype here.
Yeah.
Everything.
Well, so the CAD and CAM took me about 2 hours, about an hour for each. I did have to go back and tweak the CAM a little bit, like the soft jaws. I just did all my calcs wrong and just ran the tool through too
This
hard.
is it stuck for days earlier. Now it's 2 hours. So.
No, stuff for this stuff for days on previous projects that were similar, and that's why I'm doing this to teach you guys. Man, that's a tricky one. Somewhere around $400 a piece if you count my time.
That's,
you know.
Yeah, that's what I was gonna guess.
Yeah.
Nice Father's Day card.
So Dave, you got 4 hundos in your hand there. Run outside so you can sell it to somebody quick before Dave.
But the trick is, if you buy 100, they're like $4 a piece.
Yeah. Yeah, right. Yeah, that's what's interesting with machining is that all of, as Davey led with, all the operation, all the figuring out how to hang on to the thing, all the figuring out how to reindex it, is all of the work.
Yeah.
Like making one of those is all of the work times 10, and then making like 50 of them, it's
Yeah.
like, oh, okay, well, yeah, we push the button now and
Yeah.
it'll run again.
And that's what, like, for anybody that doesn't know, I work for Tormach. I do technical pre-sales. And so people ask me questions kind of towards this all day long, and which is why I go through all the extra detail. Like if my dad just wanted one, I mean, you could whittle this out of, with a bastard file if I needed to. But I went through all the extra motions to do all the right tool paths just to see like what it would look, just to kind of go through that process. So anyway.
So you kind of skipped over that hole you drilled, the reference hole. That's referencing in conjunction with the sides of the original stock.
Oh, you're right, and I meant to show you that in the this is the only time. Yeah, I know, Dennis. I know. I told you I went through all the motions to act like I was doing production just to do it. So to answer your question, Sean, I forgot to mention that. You can see that my coordinate, I forgot to enable the sketch while I was here, but I purposely, in that very first sketch, I purposely dropped a point. I ended up only using the point, not the actual circle. So this point is my XYZ0 for op2. And so that's the point that I drilled a hole against. And then in op2, that's the point that I use here.
First operation doesn't matter at all. The second one you have to be on that.
Yeah. So, but then I guess my point is that only works because your vice doesn't.
Right.
Because it's just a whole space, so you reference it off of it.
Yeah, the vice has to be true on axis because everything was done with the vice that's true on axis. And so, yeah, I could actually take this all out, put it in a different machine, take my vice out, spin around my head like a helicopter, put it back down. As long as I'm on axis, this hole, and then I guess I didn't show you that the Z height was the bottom of that pocket in the soft jaws. Was this the Z height that I referenced? So I would measure Z down here, and then put the part in, and then X and Y were off of this, the center of this hole.
And your material has to be square.
Square-ish.
2 parallel on the front back.
Yeah, just for that first clamping operation, yeah. And so that, yeah, so then this, and part of the thing is the soft jaws flip around, and so I did other stuff on this project, and there's a few times, like one time I actually hit go and this was in the wrong way, and I had probed it and everything, but at the last second I caught out of the corner of my eye with the shape on the screen and the shape that was, I was like, wait a second, because it would have just cut this totally the wrong way. So.
Laima and I are here to bore everyone. I'll speak.
Hey, Chris,
Yep.
is it possible to move the microphone further away? Because it's really only when people speak up that it clips a lot.
Interesting. I mean, I can cut it. Do you think the level is good except for clipping?
Yeah, the level's okay, except for clipping.
Let me find, hang on a second. I will find the podium mic and we will turn that one down.
Like right now, you're just fine.
Okay, so podium mic's microphone. So I cut the podium mic way back. So how is that now? That should be then.
Yeah, you're quite a bit quieter, but it's definitely not clipping. So maybe halfway in between.
Yeah, I was just gonna say, let me go back a little bit. All right, how's that?
Try again.
Am I pretty good now, or are we still?
You're definitely not clipping. It is still a little quiet. I've got tons of volume I can add here, but I don't know about the other folks online.
My God, maybe we'll have to write down settings or something.
Now you're clipping again.
I think Brian just pulls this thing out of his pocket every time. Plugs it in. All right. Well, I think we'll settle at this because I'm circulating around about a 7. So
This is much better than before. Thank you.
Yep, no worries. It's almost like you do audio video stuff every once in a while, or
Only once in a while.
all right. So I made some fancy slides. Let me share my screen here. All right. So Laima, of course, wanted to torture me last week and said, it'd be really cool if we could engrave some rolling pins, because it'd be awesome to make fancy cookies. So I said, oh yeah, Laima, no problem at all. We'll get the fancy rotary axis, no big deal. We got a couple of those popping around, so I'll just throw that in the laser, we'll make it go. So this is the saga of making the laser behave. So our goal, or Laima's goal, was to engrave a pattern on a rolling pin using a laser cutter. So actually, do you have your rolling pin?
We have a bunch of them.
I'll steal part of your thunder here, but you just
Like
pass
blank one or
an engraved one. Just pass. So if you want to see what we're talking about, because my picture isn't until later as far as
so you want me to just pass it around?
yeah, just pass it. Yeah, that's cool.
The ones with the handles are the ones that turned out well. The ones without handles had mistakes.
Which, well, yeah, I wasn't even acknowledging mistakes, like we were perfect. We're perfect at this. I mean, so Brian built a rotary table out of wood to be. He laser cut a rotary table on the laser to then laser things. So it's like the laserception. The challenge with that was that he made holders that were just for holding a tumbler, like a cup. And so the idea here is on the display, this cone is what fits the open end of the cup, and then there's a flat plate holding and closing the cup. We made this like, I don't know, like 6-7 years ago at least. And I have no idea where these models went for the 3D printed parts. And it also never really gripped very tightly. The cup would kind of like slide down as it rotated. And so rather than try to use this, I decided that we would instead try to get this auction rotary axis that we bought up and running. So if you don't know, the laser cutter is an XYZ, like Cartesian CNC machine. And the idea then is you drop this rotary axis in and you can use the rotary to rotate. And the laser, as far as it's concerned, thinks the gantry is moving, when in reality, it's actually rotating a rotary instead. So the catches with this thing was, we've got it for cheap, it's only 40 bucks. It's a nice aluminum slab with a motor on one end and a dead or a live center on the other end, so a bearing with a pointy bit. And it had a proprietary motor on it, or a proprietary connector, but it was a regular 4-wire stepper motor. And the problem is, well, actually, I should hit this first. So if you don't know, these are types of motors that are available in the universe. An AC motor, if you plug it into the wall, it will spin. A DC motor, if you hook it up to a battery, it will spin. A servo motor is just a DC motor with a feedback. So it has some mechanism to provide the controller with information about how fast the motor is spinning. So a servo motor are commonly talked about on CNC machines, and it's really just a DC motor with something to record movement attached to it. So you could take any DC motor and turn it into a servo motor by just putting an encoder or some data system attached to it. Then the last bit is a stepper motor. A stepper motor is like a chopped up DC motor that has little tiny sections called poles. And those poles can only move a little bit of the rotation. And so in order to make a stepper motor move, it, as its name implies, has to be stepped along to make a full circle. So in order to get a stepper motor to go, you go a little teeny bit at a time. which is the benefit of it then is you have this sort of like a feedback motor, but no feedback required. Because it's just, you're relying on the motor being able to move, and in reality, hopefully it's moving, but if it's not moving, then you don't know any better. So we're gonna dive a little bit into the weeds in the next slide or two. There are types of stepper motors, which you may have never known. So if you have a 3D printer, you have two-phase, which are 4-wire motors, these things over here. They are really common. They exhibit higher torque. They're cheap to manufacture, but they have relatively poor resolution compared to these other motors, motor types. It requires 8 MOSFETs. A MOSFET is a digital switch. So because there's 4 wires, you need 2 digital switches per wire. And by working all of these 8 switches in concert, you can make the motor spin in a circle. And if you've ever played around with Arduinos, there's a library that you import that's the stepper library. You just import this magic library and you push the button and it spins and you don't ever have to think about it. In reality, though, somebody had to write the C library that made that work, and it requires precise timing between how you're strobing these 8 switches to make the thing work. If you turn on 2 switches at the same time, it makes it short, and it instantly nukes that row of switches. Sad for you. If you spin the motor really fast, or if you unplug the motor while it's trying to step, you'll also destroy the switches. So they're relatively wimpy drivers, which is how you build stepper motors. The second type of motors are what's on our laser cutters. We have 3-phase motors, and 3-phase motors are less common, but really common on lasers because the lasers are non-contact. They're not supposed to touch anything. And as a result, the fact that they have better resolution, better precision, they have smaller step increments, and they have, because they have smaller step increments, they have more precision of movement. They are better for a laser cutter where you need accuracy, you need speed, but you don't need a lot of torque. Then the other thing is that they have, I have it kind of down here at the bottom right, this low ripple torque. That's because this has these 4 wires, and so each time it makes a chunk, it's taking a pretty big step. And then the torque curve on the motor ripples up and down a lot. The 3-phase wires, because they're smaller steps, make the torque curve smoother. And then the ultimate awesome ones are 5-phase, which I have never seen. They're 5 wires though. These biphase ones are sometimes 6. So if you see a 6-wire one, it's still just as boring type. But 5-wire fancy stepper motors have 10 MOSFETs to make them switch. So the controllers get more expensive. And they have the highest resolution and the still good torque characteristics. The reason why they're rare is because they're more expensive. So now you need 10 poles inside the motor, and you need 10 switches, so the controllers get more expensive. Those MOSFETs are the expensive part in electronics, which is probably the other reason that they put these 3-wire 3-wire motors and then lasers, because they're cheaper controllers. So they're actually saving money on the other. All right, for those of you who are visual learners, here is the same exact thing, only as a picture. So up at the top here, this is a 2-phase motor. And so it actually has 8 poles, confusingly enough. And there's our 8 MOSFETs to run it. And these are the 2 coils. So there's actually only 2 coils in the motor. These are tied together in pairs. Yep.
Why does the resolution skip around like that? Wouldn't it be 6, 8, 10? But did you say that the 8 is not as good as
8 is, well, yeah, because we're actually have only 4 poles in there. Sorry, it says 8 poles, and there are 8 pointy bits, but there's actually only 4 that are under control.
But wouldn't the same be true of the 6 then? With like 300 control?
There are, you can strobe in between them. So you get some cheating ways here, because you've actually got 3 coil sets in here. So this is only 2 coils, 3 coils, 5 coils. That's a better way to explain it. So rather than looking at this picture at the left, look at the electrical schematic. And each of these are your control element. So you got 2 coils, here are 3 coils, and then this has got 5 coils. And that's what ultimately affects the resolution. Up here, these are multiplied by 4. So this is really only acting on 2 coil sets. And so that's why these have better resolution than the best resolution.
So every other pointy bit on the top left stator.
It's the same.
Yeah.
Yeah. So you really only have 2 going on up there. Does this make sense? Sometimes pictures better, sometimes all this is better. You'll know the reoccurring theme in my slides where I have all this, and then we have one of these. So here, all this. So this is where this whole idea of having many steps breaks down, which is a modern idea of controls, which is called microstep. The picture at the bottom does not do a very good job of explaining this, but effectively, this kind of explains it. So here you've got 1 phase at 100% power. Then you decrease to 75% power on phase A, and phase B goes to 25% power. And then you slowly shift the power across phases to get incremental changes between the two phases.
And power is equal to magnetic
Flux.
force, right?
Yeah.
Yeah.
And so in this case, this is an electrical method of increasing the resolution of the motor by a lot of times. Because you can have like 100 times microstep.
So you're just adjusting the magnetic strength kind of between those two poles. So if it's like 50-50, you'll sit
Halfway
but
between them.
it's
Yep.
Not, kind of.
And so I'm sort of lying about these switches because we consider these as discrete, being on or off, but that's not how they really work. You can pulse them in order to control the amount of energy that goes through them. So now, as I talked about earlier, if you short these out, you blow up the switch leg. So now we're talking about we're pulsing these things incrementally at varying percents, up to 100th of a percentage of power. And we're not at any point shorting them out across each other, or else we'll go over current and melt it. So there's a lot going on, which is kind of why I want this route to talk about this a bit, because I think this is a thing that not a lot of people realize, like what's going on to make your 3D printer print, or what's going on to make the laser cutter move wrong. So where the hell were we?
I think you have a question in chat.
Oh, we just ignore that. If they don't want to drive over. So Dennis says, think of it like a crossfade between the steps, and that's exactly right. Audio people. So the laser cutter has what's called a RETA controller. RETA is one of the common laser controllers, and I swapped out the controller over the pandemic, and the thing stopped accepting file transfers. I think the flash memory wore out over the past 8 years or so. And so we put a new controller in it, which is why there's a new display over there and a totally new control system. The manual gives you a picture, and obviously I'm sure everybody understands what this picture is trying to tell you, how to make the motor work. So the controller supports 3 axes. And so if this picture doesn't make any sense, you can go to the manual, and then they've got it written out, and it makes not a whole lot better sense. In short, what's cool with stepper motors is that all the controllers work the same. They work with step and direction. So you have an option of holding the direction pin high or low. That tells it which direction to go. And then you just strobe the step and it moves incrementally in that direction. So even if we have a 3-phase motor or a 5-phase motor or a 2-phase motor, the controllers that run these things all work the same on the same exact protocol.
And you're talking about input into the stepper driver.
Input into the stepper driver. So on the left is our RETA controller on the terminal box, and on the right is the input of the stepper driver. And then that input of the stepper driver then goes out to these MOSFETs, and that's essentially what's happening. So the stepper motor driver is just translating a step and a direction command into those 6 or 8 or 10 FETs turning on and off really fast. So that's what this is showing you. These are opto transistors, they're optocouplers. So it's showing you an LED light, shining light onto a transistor, and that's what's then telling the stepper motor to take a step. And these are optically isolated so that you don't have a ground loop or any electrical connection between the two systems. So these are actually literally air gapped. So the controller is protected if that motor melts down by this air gap here. So someday when the stepper motor dies trying to drive the motor and it shorts out and throws 48 volts everywhere, there's a little air gap here that's going to protect our controller and our laser from also melting down. If we didn't have that there, then the whole system controls all go down. So long story short, you get the kernel 5-volt power positive and the kernel power ground, and then the differential pins. It's yeah, there's a bunch of ways to hook it up. Long story short, you dive in the side of the laser and you figure out which wires you need. In this case, what we need to do is build a little adapter. So over here, these are the stepper motor drivers, and this bottom block here is the step and direction input. So it's 4 wires, it's only 2 pins though, effectively, the differential inputs. So that's again done for isolation purposes. But long story short, essentially 2 signals come in. So we unplug this block and we make a little adapter, this guy, and that plugs us into a new controller. So this is a 2-phase controller, and these are 3-phase controllers over here. And in order for the laser cutter to run that rotary table, we need a 2-phase controller to make it drive, otherwise it ain't gonna work. So this is our connection for our motor, and this is the connection for the signals. And then we go on to the drive thing up here. So here's the stepper motor that we're talking about, this 4-wire, so 2-phase motor. And it's got a belt drive that drives this cone.
So not only do we need to know how many steps does the stepper motor take, how many degrees, so it's 0.9 degrees per step. We also need to know how many teeth are on this pulley and how many teeth are on this pulley. So some idiot, me, has to sit count them all. There are 131 teeth on this one, and there are 18 teeth on this one. And then some smart person gets out the paint marker and marks it. So if we ever have to figure this out again, we don't need to count it a second time.
Is that the one coming up with 0? Did I see that?
You watch yourself. You draw a fat line through the 0, it turns into a 1. Yeah, I counted 130 and it turns like nothing. Yeah, yeah. So then the next thing you have to do is sit down and do some math, because we need to tell the controller how many steps does the controller need to take to make one full revolution of our whole travel area. So in order to do that, we bust out Excel, of course, because we're lazy and it's math. And we cannot forget this controller is a fixed microstepping mode, so it has 10 microsteps per step. So each step here is 0.9 degrees of motor rotation. And then there are 10 microsteps per 0.9 degrees. So this is 400 steps per revolution of the motor. Then we've got 18 to 131 teeth. 130 was my earlier method. And so in order to rotate the pinion one revolution, we need 4,000 steps. In order to rotate the whole cup one revolution, we need 29,111.11 steps.
What's the pinion?
The pinion is the little one, this guy. And then this is the sprocket out here. So this is a gear terminology of little one and big one. So the pinion is on the motor and the sprocket is on the
That's 29,111 micro steps.
steps.
Well, steps to the pulses to the driver.
Pulses to the driver, that's right. Which, yes, you're correct, are micro steps plus the incremental reduction, all the other stuff. But yeah, so effectively these are 29,111 steps to rotate the whole thing, which is the micro steps.
And you just throw the 0.11 out the window, right?
Oh no, we put that in. We want precision here. Look at how many decimals we've got. We got lots of decimals. Yeah. Oops, somebody here. Anyway, so then we have to do the software configuration. So we need to take this number, put it in the software, and make the laser do what it's supposed to. So all the laser cutter softwares are the same. And essentially you find somewhere fancy in the control software and you put the right number in the right spot. And then it's happy. In the case of the software we're using, Lightburn, it actually has, because it's complicated to figure out this menu, they built a smart menu that just does the rotary and then swaps out the number for you on the controller. So it goes in the controller in
Then
here.
it would continue, and then it wanted a credit card.
My parents. My mom and dad. Anyway, so long story short, we get in here we put in the right number of steps per revolution. And then this is the next most important thing, which Laima had lots of fun trying to figure out. And that is the plain old boring math where you put in your object diameter, and then it'll tell you your circumference of your object, which is really important to get your graphic to wrap all the way around. The most complicated thing to do is a graphic that wraps all around the object, because you have to take the exact number of steps to get it to go all the way around and be perfect. And if you don't do that, then your graphics won't line up, which are the defect ones. Which we spent a lot of time trying to figure out why they did not step correctly, they did not land out where they were supposed to on the steps. And so we put this in, just like Davey's talking about, you have to line up the axis. And so we eyeballed it, and it turned out just fine. But we needed to make sure that the laser is moving evenly straight across on the rotary, otherwise you'd end up skewing your graphics. If you do a cup, you actually tip this whole rotary axis this way to make the cup plane flat. So we had a tapered cup, then you spin the tapered cup in order to get and tip it, make it flat and plain to make it work out. These are round, which actually is our one saving grace, is that they're much easier to do than cups are. So the laser runs back and forth and slowly increments through the steps to move it out of the way. And then hopefully we get on it. The challenge that we had a bunch of was trying to get the thing not to screw up as it was going around. So we were trying to remeasure and recount the steps and refigure out the encoder and figure out why the thing was like not consistently stopping for long.
Did you ever figure anything out there definitively?
We did very definitively figure it out. So the giveaway one was when we engraved one and it changed, and then it changed back.
Just have a design catalog.
So on one side of the rolling pin, the design is like double the length, and on the other side of the rolling pin, it's really tight. And so as it was rolling around, it had more air and then less air, which immediately told me it has nothing to do with the electronics and the motor. It has everything to do with the stupid rolling pin slipping.
Oh,
So as it went over one side, it loosened up. And as it went over the other side, it tightened up again. And so we added on a whole bunch of steps, or added on a whole bunch of distance because the rolling pin was literally rolling over itself and slipping. And the first one we started with happened to be the one that had wood mats and not a plastic insert. Because the plastic inserts, and it was a huge hole, so it hung on really good. So we ran the first one, it worked great. And then every one we did after that worked terribly. We were trying to figure out why it was not working so hot.
so your resolution was to clamp harder, or what was the fix?
Put some tape on it. Probably
Recording live? I don't want to record live.
Oh.
So, Chris, how did you deal with the limit switch issue? Did you just manually trigger that every time you reset it?
We just ignored the limit switch. So in this case, that was the other thing I explained to Laima was that when you boot up the laser, you have to manually push the limit buttons or the limit switches that are in the laser cabinet on the original axis in order to tell the laser that it's successfully homed in order to make it work. And the next step is, well, actually here, we'll get to the last slide.
So do I understand from what you just said that you don't have a 4-axis laser, you have a 3-axis laser, you can switch that 3rd axis?
Yes, we have a 3-axis laser.
Okay.
And then we're swapping the axis. So the deliverable on all these is the cookies, which Laima, of course, brought bribes to the crowd. The idea then is when you roll this thing across, you get the imprinted cookie pattern. And our next step is to put a 3-phase motor on the drive and take out all of the work because that way we can just go back to having a regular 3-phase motor where it belongs. Now the funny bit was, my box moved. The funny bit was I looked on eBay to try and find a motor, and all the motors were from overseas because that's where everybody manufactures this stuff. And they were like $60 a piece plus like $30 for shipping. And I found one place in the US that had them, and they were in Madison, which is hilarious. So they have like 100 motors. I have no idea what they're from. But anyways, we went and bought them. They're an identical match for what's already in the laser cutter. So the next step will be to install this motor in the with an adapter plate into the rotary, and that way we can set this up, and then we'll just plug and unplug the rotary rather than having to go through it whole part of the apart.
When you use these motors, are you gonna have to reset all that math, or is it gonna be different control?
Oh, reset the math. You just recalculate it.
How much was the cookie worth?
It's worth not getting code switching mask.
Probably $4.
Well, they're really yummy. Yeah. And that was it like days of time that you all worked together on this?
No, this
I
was
think you put more effort into it than I did.
it was
I
like
just showed up.
6 hours. Sean did most of the work. Sean got stuck turning the little points on for the cones.
But it sounds like it should have made it rougher, you know, they smooth that.
Yeah, we made the taper really smooth. It is good. It's a good point. Could have ran the.
I mean, is that where you put the tape?
Yes. Yeah, it was real.
It's really elegant, way more than just engraved. So you think
It's also a pain in the ass. It's a special event cookie. It's not an everyday cookie because you have to boil this. So you boil it for a couple hours before you start, and then you have to wipe off extra oil, and then it suck it. This guy said, "This is too fine," so I have to prove that it works. But I did also spend with the wire.
I teach at a school for the blind, so it's almost gonna be on my cookie. Some of my students.
You can have the rest of it.
Oh, good. Oh, wow. Like everybody else, I'll sell these for $4.
It's a good thing.
Thank you. Wow.
Same you can put your mask.
Oh.
Yep. Don't get in COVID
Don't
here.
get
That's
them
our
all
only
right now.
requirement. Anybody got any questions? More than you ever want to know about.
Oh,
stuff.
I do, sorry, spaced out for a second. How on earth did you get that clean again, and will you be able to do it again?
How did I get it? Oh, with a wire brush.
After you made the cookies?
Well, so if you boil it and you only work with super cold dough, it's not a problem.
Okay.
But if you take shortcuts, it becomes a problem. But yeah, just a little wire brush
Okay.
works fine.
That was my first thought, was like, that's got gross cookies in it. I actually looked and I didn't see it.
Didn't feel like a canvas at all.
I mean, if you want to take another look, this is literally the one I use.
No, I'm just curious.
So did you roll with a regular rolling pin to get the thickness and then
Yes.
one final pass?
Yes.
Does it damage the impressions much?
It depends on what the metal or what the wood is made of. So this one is made out of something softer. And I lost bits of the wood just while sanding the laser cutter stuff on it. But the other ones are harder. I didn't use it. I did not use the breaky one.
It's extra fibers. Any other?
When I was thinking through this, is there any way that you can laser cut a cookie on a really low, like, power setting?
Didn't you do that, Scott?
Oh,
can do
well,
that?
there's lots of
That's
gingerbread,
awesome.
yeah. We laser cut sheets and sheets of gingerbread. Like, not to bake them, but it's already baked and then we cut it shapes out.
You got somebody at the door.
Yeah, it's a bad intelligent.
Was
Yeah.
that Scott? No, it's something.
So you can do that. You can put designs in the laser cutter.
So you can engrave cookies and it tastes terrible.
I was gonna say, what's the?
So the problem is that the laser beam is like multiple thousands of degrees. And so it can't like caramelize something. It just nukes the hell out of it. Carbon. Yeah, it's basically carbonizing it. So the problem is with the cookies is that you can't like mark it without really pouring it. It's just not good.
Did that happen to your cookies,
Oh yeah.
Scott?
Yeah, well, we were doing more construction with the gingerbread.
Oh, okay. I get it.
So yeah,
What he's
Scott was.
looking for is a CNC router.
I was thinking about that too. but-
When you like design the roller thing, you usually just do it on a flat, on a model that. As you did it, just square pretty much.
I measured how wide it was.
Yeah.
And then you figure out. the layout.
Yeah, and that is actually something I should mention is that every one of these we measure the rolling pin to get the actual diameter, and then we scale the design to match the circumference. Because we want it to wrap all the way around, we don't necessarily care how big or small it is within reason. And so if we really wanted to shrink it down, we'd have to make the increment change of the number of squares going around. So
Even
we got,
actually see how my math does not great.
It turned out-
Wider edge, the wider border.
So I was gonna say, I wondered if the borders were like that way you have like a top, I imagine you just did off a sheet and not cut a piece of it.
That is absolutely the way to do it. Yeah, no, but it's because I was buying these at the thrift store and some are finding $50 less, so they're all different lengths and different.
$2.
So did you pull the handles off of those and stuff?
Yeah.
But they're made, how accurately do you get to measure the diameter?
To the 1,000. Well, actually, it turned out we didn't need to measure them that accurately at all once we figured out that they were slipping. Because these were finishing like right on once we taped them. It just, before that, it was all over the place. We were trying to correct the step ratio to project like 4-inch change, assuming that something was just wrong. And it was just slipping. But yeah, once that one, it was consistently slipping on the first couple. And so it was hard to figure out that it was slowly growing. But then the one when it grew a ton and then shrunk a ton, then it was super obvious that it was slipping. It had nothing to do with electronics. So, but yeah, you can see where that one just gets chopped off at like a third of the way in. There's one that went around and it was way longer than it was before. They were $1. We were learning.
No, I mean, for time.
Did you decide on the depth that you like? Or how much you kind of branched out?
The one that we did worked out perfectly. I thought it was visible on the cookies and it wasn't too terribly difficult to clean.
Yeah, there's a rolling pin setting stored. So if you want to do your own rolling pins, I mean, it's kind of Laima's proprietary knowledge here, but I'm willing to help, I suppose. But yeah, it's the maple. As long as the density of them they're all should be maple pins. Usually, they work out. It's pretty consistent about 8-inch deep. Any other questions?
Good double clap for that.
You guys have anything else to share? Otherwise, we can go around and say who we are, sitting in whatever else. All right, we're gonna
ditch all the Sioux folks, so thanks for coming. We'll see you guys next time.
It's good to see you all. Take care.
Have a good night.